Let's get started. I'm Nigel Goldenfeld, Professor in Physics. I've been here for about 3.5 years. Before that, I was at the University of Illinois in Champaign. And so I'm teaching you about emergence. So thanks for signing up for the class. What I want to do today is I would like to just go over a few sort of housekeeping things about how the course will work and show you a little bit about the website for the course and Canvas and some of the exercises that I've already put online that you can start working on. And then I want to give you a bracing and exciting introductory lecture that will make you realize why this class is the most exciting class that you could possibly have chosen to take. So let's get started. So first of all, this is the Canvas page, and you can read a little bit about what the course is about. You know something about it already, I'm sure, because you wouldn't otherwise be here. But I've updated this a little bit since you probably read about the course. So I want to just go over some of the things that are different. In the past, when I taught this course, it has mainly been to condensed matter theorists. But this time, my plan is to include a little bit more about biological emergence, particularly biological pattern formation, and also non-equilibrium pattern formation. So how many people here are here because they desperately want a full condensed matter theory course, no holds barred, and nothing to do with soft matter, non-equilibrium biology at all? Anybody like that? How many people are here interested in biology? How many people here are interested mainly in condensed matter physics? Okay. How many people here are mainly interested in anything else, but they realize that emergence is fundamental to everything that goes on in science? Okay. Okay. So what I see is basically about half the class wants to learn condensed matter, the other half wants to learn about biology and a little bit about biology. Now, most of this class is going to be about condensed matter because I think everything that I'm going to teach you was first discovered in condensed matter physics. And it's important to know how to use that. And but the people who are doing condensed matter, often they will see that when I start talking about biological information and biological emergence, they will see that the approach that I'm going to be talking about is very much the approach of a physicist, not the approach of a biologist. And so by that I mean that it's very quantitative. And it'll take you into areas of non-equilibrium statistical mechanics that you probably haven't been exposed to before. Okay, so that's what we're going to do. I'll go over the syllabus in just a second. We will have about 4 homework assignments, and the final is a term essay. And the lecture notes for the course are all online. So most of them are, if you click here, you will be able to download the lecture notes, which were the basis of a book that I wrote, which is used throughout the world, including here. And then there's other unpublished material, which will one day be a book, and that is available over here. And then if you want to know what the class was like in 2024 when I taught this, those are also online. And you can see them not here, but in another site that's linked to that's linked here. And then lastly, there is a web page of exciting movies, which I invite you to explore. So these are movies about the phenomenon of superfluidity, in particular, which we will talk about in the class, and then also dynamics of quantum vortices. This is work that I did many years ago. It's not published, but it'll show you how to visualize some of the phenomena that you see in quantum fluids, and where you have emergent degrees of freedom which have topological structure. So last quarter, I taught a course on emergence and phase transitions, and those lectures are also on YouTube. So you can just look for those. And that course was all about the modern theory of phase transitions, so the normalization group theory. But it starts off with using mean field theory. It assumes that you have no basic prior experience of looking at phase transitions before. Some of the people in this room have taken that class. So I'm not going to say too much about it, but if you want to learn about phase transitions in the normalization group, going from the regular classical statistical mechanics all the way through to a little bit of non-equilibrium statistical mechanics and how to even use the normalization group theory to solve differential equations, that's all in this course anyway. Okay, so let's go back to today's course. So if you're looking at this, if you're looking at the home page in the student view, you will see a few things here. So first of all, there's an announcement just welcoming you to the class. There is a survey here, which you're supposed to take just so that you can, so the university knows that you've started work. I don't really know why that happened, why you need to do that, but I'm told you should do it. So you just go there and just click a button or something, and that's all you need to do. Then what I have here are two things. So one is homework 0. So let me tell you what that is. So this is an assignment. It doesn't count towards the final grade. And the purpose of it is to teach you how to read a scientific paper in 5 minutes. Well, you can read it in less than that, but 5 minutes is a good start. So it's not an assignment that you should do as a grading thing. But you should definitely do it because it will teach you a lot. So if you click on the link, you will get a page not found. So I will fix that. So that's really weird. Okay. So anyway, I will fix that. Anyway, it's a homework assignment that walks you through how to read a paper in about 5 easy steps, and then asks you to choose a paper and then write a simple 1-page report about it. And I encourage you to do that for yourself, because how many people here are PhD students? Some of you are. Some of you are undergraduates. Great. Okay, fantastic. Even better. Okay, undergraduates have to read lots and lots of papers. So especially if they want to get into research, and PhD students have to read even more. And the way that this class is evaluated is 50% homework assignments and 50% essays. The term essay at the end, and you will read papers for that. And learning how to read a scientific paper and actively read it, asking questions, will improve how you learn about the subject. So, I'm not going to go and walk you through it, but I do ask that you do that assignment. Then there's another assignment which I suppose will probably also not work. But let me just see. No, that one works. Why does that one work and the other one doesn't? Don't know. Well, it's a mystery. Anyway, this is about second quantization. Now, why am I giving you a homework assignment? It's a worksheet on second quantization. It's not something that you have to do for credit. Some of you will have seen second quantization before. Some of you may not have done. If you've never seen it before, then this will teach you how to do it, but it's not intended as like a basic explanation of the understanding of it. You would need to have seen it in the class previously. If you haven't seen it before, then I can give you some suggestions of where to read about it. So we're not going to be using this right now, but later in the course, about halfway through the course, and so in about 5 or 6 weeks' time, we will want to look at order in interacting Bose-Einstein condensates, looking at how superfluid order arises, how systems are ordered, quantum mechanical systems order. And so we will use these very simple methods, which are not nearly as sophisticated as quantum field theory, but nevertheless are all you need really to be able to understand how to study emergence in quantum systems. So that's the first use case for this. The second use case for this is more surprising. So I will be talking a little bit about ecological pattern formation, how systems make patterns in biology. And I am going to be using this formalism, this quantum mechanical formalism, to study ecological systems. Okay, so you're going to say, wait, we're going to do quantum mechanics for ecosystems? Well, in a sense, yes, because here's why. When you do quantum mechanics, you have things that come in quanta, such as energy or angular momentum or momentum and so on. So we use operators to add discrete amounts of energy or momentum or particles to a system. So when you have integer valued variables, that's what we mean by quantum mechanics. Things are quantized. Classical things are also quantized. If I have creatures living in an ecosystem, sheep, wolves, fish, whatever it might be, they actually move around and they can give birth, they can die, they can eat each other, all sorts of things like that. Those processes change the number of particles by plus or minus 1. So if you're going to try to understand how pattern formation occurs in ecology, it turns out that if you try to do this without doing this method, and if you take into account stochasticity, randomness, it's impossible to do it by any other way other than using the mathematics of second quantization that was originally developed in quantum mechanics. So I will show you how, in very simple ways, how one can go about and do that. So this worksheet is one that you can work through, and if you find it tricky, if you haven't run into it before, then I can help you so that you can learn it. And it's really neat. If you've never seen it before, it's really neat. How many people here have not seen second quantization before? So two of you haven't. Okay. So I'm quite happy to work with you to show you how you can learn about it, and you won't find it difficult, but you will find it interesting. All right. So that I think is are the main things. Oh, and there's one other thing I want to show you. I have a homework assignment for you, but it's a really easy homework assignment. The really easy homework assignment is to take this computer simulation. And it's a simulation of order. The yellow means it is a magnet where the spins are pointing up. The blue is a magnet where the spins are pointing down. And the thing you can adjust is the temperature of this magnet. And the homework assignment is very quick and a lot of fun. It just asks you do some experiments, and I suggest to you what particular experiments that you can try, and you can see some of the phenomena that we're going to be talking about in this course just from looking at this computer simulation, just by playing with the temperature. So we can scan through the phase diagram of the system, and we can learn a little bit about some of the phenomena to do with emergence. So that is homework assignment number 1. All right, so you can basically do that anytime you like. Well, when I say anytime you like, I don't mean like right now, but I mean you can do that, and I made a due date for that, which is April the 10th. Okay? But because what we'll start doing is every 2 weeks I will issue homework. There'll be 4 homework assignments, depending on what the class is interested in and people's interests. I will adjust those things. What I usually do with the homeworks that I send out is I make one assignment mandatory, and then the other assignments are all optional. And you don't have to do them, but if you want to have mastery of the subject, you would do some of the other assignments depending on how much time you have. If you want to just learn a little bit about the subject, but you don't want to have you just don't have the time to do a lot of stuff, then you don't have to do those problems too. So it's easy in that sense, and it depends on what people want to get out of the class, what they do. Okay. So that is the basic structure. Now I want to tell you about the syllabus. So, okay, so here is the syllabus. Today we're going to talk about emergence in general. I'm going to just give you a lecture about why this course is interesting and what its scope is. We will then start talking about systems with continuous symmetries. I'll explain what those are. We'll talk about stochastic pattern information for equilibrium. In particular, I'm going to talk about biology first. I want to talk about how we get emergence order in biological systems. And then we'll talk about what happens in fluid mechanics. And then with the last lecture, I will give one seminar, the type lecture, an extended seminar type lecture, around fluid turbulence, hallucination, the cortex, or evolution, just depending on what the class is interested in at that time. So my background is in condensed matter theory, but I work in many different areas of science, ranging from biology to condensed matter physics to fluid mechanics to epidemiology to quantitative finance, pretty much high temperature superconductivity, all sorts of things. So if you have any questions about science at all, it's quite possible that I might know something about the subject, and feel free to ask me about it. Okay, I want to also show you how I keep in touch with the class. So I will set an office hour, but I'm not quite sure yet when that's going to be. Usually it is Tuesdays at 11, but I might change that depending on what your schedule is. But in any case, what I like to do is use Microsoft Teams so that you can ask questions and interact with me, send me instant messages anytime you like in real time. Many of the students do. So I will be adding lectures and the videos of the lectures in this channel. I have here a channel called Articles About Emergence, where I post articles that I see which are relevant to the class, and you can do so as well. This is the channel on second quantization. So, for example, here I make channels for every homework that I produce. So you can see here, for example, in I don't know which what this one will have, but for example, here's a homework one from the class I taught last quarter, and one of the students was asking a question. Actually, this is one of the graduate students was asking a question about something or other. So they just post a question there, and either this grader answers it, or the students answer it, or the students in the class, or I answer it. You can send chat messages. So we will have channels made like this for all the different homeworks, and then in this one here, I will post the lectures and the lecture notes and videos, and also if I have any corrections to the lectures or something comes up and I want to tell you about, you should look at this to do with what I talked about in the lecture, you can see that there, and you can also post questions and ask questions about that. So do get Microsoft Teams. Surprisingly, it doesn't suck, and previous classes have found this to be very useful. Okay, so that's all the introductory stuff. Anybody have any questions before I get started on telling you about solids? Okay. All right, so this lecture is on Introduction to Emergence, or why you should take this course. Okay, so yes, okay, got it right. Okay, so let's move this up. So the class I taught last quarter is not a prerequisite for this class. but people who want a thorough understanding will find it interesting. That was a course about impossible things. Okay? Emergence is something that shouldn't happen. People still don't really understand why emergence happens in many fields of science. People still don't really understand what it means in terms of how we make models of systems. So emergence shouldn't happen. Then I'm going to tell you what we did in the class was we discovered that linear response theory breaks down at phase transitions, meaning when you apply a perturbation to something, you expect that the system to respond proportionally to how strongly you perturbed it. If I hit something, it'll make a noise. If I hit it louder, it'll make a louder noise. Okay, that's called linear response theory. It breaks down when you're near phase transitions. In fact, perturbation theory breaks down at phase transitions. Dimensional analysis seems to break down. In fact, the idea that if something is small, you can neglect it, common sense ideas, all of those things break down at phase transitions. And the other thing I'm going to tell you is that even very precise predictions are obviously wrong starting points. And that's a very surprising thing. And that's what phase transitions in the normalization group was about. This class is not about that. So this class is about what happens when you've already had a phase transition and the system is now in a state where it is ordered and where there are emergent phenomena. So I like to think of that as basically saying how you get something from nothing. Okay, that's what emergence is. It's how to get something from nothing. So I'm going to show you that complex interacting systems have similar properties. Complex interacting systems have similar descriptions. And let me give you an example of that. I might make a model of a theoretical model of a superconductor. How many people here know what a superconductor is? How many people have heard of a superconductor? Okay, they've just heard of them. Most people don't know what it is. That's usual. Okay, but roughly speaking, a superconductor is a thing that conducts electricity without any resistance. It also does a lot of other things too, and I'm not going to talk so much about superconductors in this class, but they experiment in fields. They have other weird collective effects, and so that's superconductivity. Very striking, macroscopic, quantum mechanical phenomenon. Okay. Okay, that's how you describe superconductivity, and there's a way to do it, which I will teach you. You can use the same methods that are used in superconductivity to understand this kind of order that you see if you, let's say, go to a restaurant and order a bowl of miso soup. And the miso soup will arrive at the table, it'll be nice and hot, and you will see in the miso soup little hexagonal patterns and miso stuff circulating around in the miso soup. So the miso soup spontaneously forms patterns right in front of your eyes. You can also do something else. You might say, okay, I'm going to order salad. So you get some salad and you get some oil and vinegar and you add that to your salad to make it taste nice, because salad only tastes nice when you pour acid on it. Okay, when you eat such a thing, you might be talking to your friend who you're at dinner with, and after you've been talking with them for a while, you forgot to eat your salad, and you go and look at your salad, and you see it's got all these nasty, unattractive blobs of oil and vinegar separated on it. How that process happens is also described by the same formalism that we use to describe superconductivity. Okay, it's amazing that that works. Okay, so we're going to be talking about top-down versus the bottom-up approach to science. So the bottom-up approach is what you've been taught so far. The bottom-up approach says this: if you want to understand something, figure out what it's made of. Okay, so it's made out of atoms or molecules or quarks. Okay, so you know what it's made of, and then once you know those bits, you just put them together, and then you understand how the thing behaves. Completely wrong, completely failed. Okay, the failure of that mode of thinking is what this course is all about. So that's called a bottom-up approach. Start at the bottom, start with the building blocks of matter, and then put them all together, and then you understand everything. Okay, completely wrong. Then, and then we'll talk about excitations. So if I have a system that has emergence and has order, when you hit it, and it makes a noise, the way it makes a noise is it creates excitations. Those excitations can behave in very common ways, more or less independent of what the system is. There's a unified way of thinking about how systems respond when you excite them. And some of those excitations are very interesting because they behave like particles, but they're really actually collective effects. So when you say take something like a superfluid and it's above absolute zero, it forms a quantum condensate, which I'll explain to you what it is. But that quantum condensate, if you're at a finite temperature, will have thermal excitations, thermal fluctuations. And those thermal fluctuations will behave like little particles, they'll behave like particles, but actually they're made up of all the actual atoms in the system, all conspiring to act together to form a thing called a quasiparticle. And these are collective excitations, they're not just things bouncing around which are the things it's made of. So that's the first thing. You are listening to these sort of excitations right now because I'm sending you sound waves, and these sound waves are actually behave in some sense like particles. In low temperatures they are quantized, and they behave in ways that reflect the properties of a system, the collective properties of the system. Some excitations can be topological, so you can have weird objects which have non-trivial topology, and those objects, we'll talk about what those are. Those objects also are excitations, and the mathematics you need to describe them and the phenomena that they give rise to are also completely revolutionized physics, starting from about 30 years ago when they were discovered. The Nobel Prize in physics was given in 2016 to people who pioneered this idea of looking at topological order, and we'll talk a little bit about that. And then if we have time, we may talk a little bit about the dimension reduction complex problem. So anyway, so emergence is very widespread. So who cares about it? So we all should care about it. So here is the phase diagram of life. Okay, I'm not going to go into how this phase diagram was worked out and how we measured it experimentally. But what I want to explain to you is that this is time going down here. So we live in this era up here, and this era here is like 4.6 billion years ago is when the planet Earth was created. Life started about 3.8 billion years ago. That's roughly around here. That's what most people would say, that's where life started. LUCA stands for last universal common ancestor. It means the organism that we're all descended from, either a community or a single organism. But it wasn't the first ancestor of life on Earth. There's all this other life here whose record has now disappeared. We can't really access it except indirectly. But what we do know is that there's an earlier phase of life where the life actually behaved in a collective way. Whereas here, you're seeing the family tree of life. This is just a whole family tree, but for species. Life doesn't have to have a family tree. Life can actually have a network of life. It doesn't have to be a tree. And that network effect actually is how life evolved so rapidly in the planet. So this is so life itself is an emergent phenomenon. Here's another example of an emergent phenomenon, and this is why this may be the most important class you will ever take. People are trying to understand global climate change, which, as you know, is happening at an ever-increasing rate. What people would like to understand are early warning signals of phase transitions in climate systems, and we don't understand those things very well at all. There's a lot of work going on in this area. And so it turns out that climate and the phases of the Earth are themselves ordered systems and are collective interactions between the ocean, between the air, between the organisms that live there, between the way that they absorb carbon, the way that they the way that they metabolize, and so on. So, what are complex systems? Well, here's how you can recognize one. When you see one, they have strong fluctuations. The dynamics is unpredictable and non-linear. There's multiple scales of space and time, and they have something that is emergent, right? Like us, for example. We ourselves are examples of emergent objects. We have multiple scales of space and time in our bodies. We are creatures. We have organs. We have tissues. We're made up of cells. Inside the cells, there's all sorts of biological processes going on. Multiple scales of space and time happening just in us. And then complex systems also have active components. Mostly what we're interested in, at least in modern research, what we're interested in is non-equilibrium complex systems, which have active components, which can evolve, which have interesting dynamics as a result of the fact that they're being driven. So every ecosystem in the planet is, not every ecosystem in the planet, most ecosystems in the planet are driven by what thing? What drives most life on this planet? Gravity? No. Well, what provides the, why did you say that? Are you thinking about what provides the inputs to the system? I mean, we certainly respond to gravity. That's absolutely true. Our response to gravity is very different from that of, say, a hummingbird or something like that, right? But I want to know, what is the thing that powers ecosystems? What powers living systems? Heat. Yes, in some sense, food. Yeah. Those are all good answers. Where does the heat come from? Say again? The sun. The sun. There are many sets of reactions that power us, say food, for example. Okay, but ultimately, for most ecosystems, it comes from the sun. If you're eating something, it's because it's, if you're not a vegetarian, you might be eating a creature that lives on grass. Okay, well, how did that creature get its energy? The grass got its energy by photosynthesizing and so on and so on. There's organisms, there's ecosystems on the planet where they never see the sun. Microorganisms that live in rocks beneath the sea surface, beneath the sea floor, excuse me. Those organisms never see the sun. They live on heat. They might get that heat from radiation. Their timescales are incredibly slow. They might replicate once every 100 years, as opposed to, say, an E. coli, which will replicate in, say, 20 minutes. So the energy structure of the ecosystem has got multiple scales of space and time, and it's interesting to track it. Okay, why are we looking at complex systems? Why do we care? Well, when you develop the sciences, you pick the low-hanging fruit first. So the easiest thing to figure out is an apple falls from a tree and hits you on the head, and you're Isaac Newton. So you might say, okay, fine, why did it fall? Just like you said, it's gravity. But if Newton had been a biologist, he might have said, why do we have apples? And then you really got stuck. Okay, but understanding why a single apple falls due to gravity, that actually turned out to be a solvable problem. He had to invent calculus to do it and stuff like this, launched modern physics, but that particle-based approach, thinking of an apple as a particle and then figuring out what happens, that's the reductionist approach. So you pick the low-hanging fruit first, unless it falls on your head, and that's what we do is reductionism. We look at the parts of systems. But ultimately, you're going to end up with systems where you have strong interactions, where you have emergent phenomena and complexity. And so in the sciences, the first things you're going to do, the easiest scientific things that you can study are going to be reductionist physics, just looking at the parts and seeing how they behave. How do gas particles fly around in this room? Okay, they both sort of bounce into each other. They don't do anything that's particularly exciting or interesting. But then eventually you want to look at things that are strongly interacting. And this whole field started by Phil Anderson in the 1970s. I mean, he didn't really start the field, but he wrote a very influential essay talking about symmetry breaking and the hierarchical structural science, and talking about how reductionism, the idea that you just break things up into little pieces and then just look at those pieces, how that is not really misses behavior that we would like to understand. Okay, so now I want to talk about emergence. So we're going to do an experiment. Okay, so here's the experiment. Okay, so I'm going to do a bit of the experiment over here, and then you're going to do a bit of the experiment yourself. Okay, so stand up so you can see the front. I'm going to show you something that is completely amazing. Okay? Completely amazing. I want to make sure you all see it, because I don't know if you've seen it before, but I want you to all see it. So everyone can see. Okay, so here's my finger. Okay, and see this pen, this marker. I'm going to push it, and it moves. Isn't that amazing? Let me do it again, just so I didn't fake it. It actually moves. Okay. Now you should be astonished about that. So let's think why you should be astonished. You can sit down now. You all saw that this thing moved. Okay. So I want you to do this. Get your finger, same finger that I used. Point it up. Nobody do that. Okay. And I want to see if you can push the ceiling. Okay. So push up. Anything happen? Anybody feel ceiling pushing back? No. Yeah. No. When I push this, I feel it on the end of my fingers and it pushes back. So you're saying, well, of course, I wasn't really touching the ceiling. You're touching the air, and then the air is going to the ceiling. And so the question is, well, when you push the air, why didn't that force get transmitted through the air and then push the ceiling? Okay, so you're saying, well, one's air and one is a pen. But if I write down the physics of this, I'll say, well, what is a Hamiltonian of the system? So the Hamiltonian of the system is the energy. So I can write it down. I've got the kinetic energy of the particles in this, kinetic energy of the particles in the air. I've got the potential energy. The potential energy comes from interactions such as van der Waals interactions or Lennard-Jones potentials, all sorts of interatomic, intermolecular interactions, but they're all the same. And yet when I push the air, my finger just goes straight through without any resistance. When I push the pen, it actually moves, but they have the same physical description. So there's something we missed. Okay, now let's try to think about it. So here's a bunch of particles bouncing around in a box. They're atoms. They're in the fluid state. Okay, so the answer to the question about why this didn't work is because, let's suppose I suddenly cooled the room down to, I don't know, liquid nitrogen temperatures or something like this, maybe a bit lower. Okay? And you were still miraculously alive, you know, in some spacesuit or something. Now, if you did this, what would happen? I'm below liquid nitrogen temperature. I'd feel pushback because the air would now be solid. And I would push it, and it would push the ceiling. So the answer is, the thing that's different is the temperature. Okay, so I've got particles in a box. I have low temperature, and what happens then is a crystalline solid forms. And let's have a look about what a crystalline solid is. Well, if it's crystalline, it will have a periodic crystal lattice, and it will also have shear rigidity, meaning I can try to shear it to form it in a particular kind of way, and it will resist that deformation, whereas air or fluid will not do it. So the low temperature phase is different from the high temperature phase. So why is it interesting? Well, because the underlying physics of the crystal is exactly the same as the fluid. The total energy is the kinetic energy plus the potential energy. Lowering the temperature hasn't changed the interactions between the atoms. And yet, the atoms have somehow conspired to do something different when they're in the solid state. So, conclusion from this little thought experiment, although the pairwise interactions between atoms didn't change, the correlations between them changed when the temperature was low. Why do I say correlations? Well, if the atoms are in a solid, and this atom likes to sit right next to this one here, and this one here is next to this one over here, and this one over here is next to this one, and they stay in that position. They conspire to be in fixed distances from each other. We say that they're correlated in their positions. So the correlations between them changed when the temperature was lower. Because when they were a gas, this particle is flying around, this one is flying around, and whether this one is next to this one or not changes as a function of time as they fly around and bounce off the wall. So the correlations changed when they were lowered, and the solid state emerged as if by magic out of the fluid state. So why is this a big deal? I'm going to explain this now. The solid state has its own new laws of physics. Okay, listen to what I just said. The solid state has new laws of physics. Okay, I'm not being facetious. So let's have a look. Here's a solid state. If you were to open up a solid state physics book, you would see that I've got a picture of a solid that looks something like this. So the red things are atoms, the springs are the interactions between the atoms, and the thing forms a solid. And then if I were to hit it from the side, hit the atom over here, what would happen is these things would vibrate. You would see sound waves propagating through the solid. This is the textbook picture of a solid you would see in an elementary course on solid state physics. So the thing about this is that the new laws of physics are the following. These atoms have springs between them. Where do those atoms come from? Sorry, where do the springs come from? They're definitely not there in the Hamiltonian particles bouncing around in a box with kinetic energy plus potential energy. The springs between the atoms are emergent. The elasticity of a solid is a result of the springs being there, and that is something that has emerged from nothing. And if you didn't know how to compute it, you wouldn't know to put such a thing in. You would think everything would just be a gas or a liquid. You wouldn't know that such a thing could happen. So the new laws of physics of the solid compared to a liquid are that it has elasticity. The response of a solid to external disturbances completely different from that of a fluid. And where do these new laws come from? The collective statistical behavior of the atoms. Okay? They're not put in by hand. They came out by magic. That's what emergence is. Okay, so you're going to say, okay, fine, but is this really new laws of physics? After all, what you've just told me is that if I know how to compute properly, work out the statistical mechanics of a bunch of particles bouncing around in a box, I can predict that they will form a solid, and it's true that I can, and I'll be able to predict the rigidity and the elasticity of the solid. So that's true. But the thing I want you to think about is this. At the level of description of a solid, these interactions cannot be detected. So let me ask you this question. Who figured out that atoms exist? How do we know that atoms exist? Who was the first person to really convince everybody that atoms existed? So today we know atoms exist because we can look at them with an electron microscope. You can literally see the atoms, okay? But 100 years ago, well, 120 years ago, one couldn't do that. How did we figure out that atoms exist? Okay, easy question. Who figured it out? Okay, just the same person who figured out virtually all of modern physics. This person didn't get the Nobel Prize for this. He got the Nobel Prize for something else. He could have got 6 other Nobel Prizes, but he didn't. Who was this?
If you say invented all modern physics, I want to say Einstein.
It's Einstein. Yes, yes. You're right. Yeah, I'm trying to give you some hints here. Yeah, exactly. It was Einstein. He didn't figure it out with the electron microscope. He figured it out from statistical mechanics, and the experiment was done. What he figured out was what's called Brownian motion. if you look through a microscope at bits of pollen, as Robert Brown did in like the 1820s, what you see is that these pollen particles, which are dead, are moving around in some weird, unpredictable, jerky way. And this was a real puzzle because these things weren't alive, but they were behaving as if they were alive. And Einstein figured out where this came from and how it reflected the existence of atoms. And then Perrin did the experiments, and it was confirmed quantitatively, and that's how we know that atoms exist. So, so the thing is this then, you might say, well, it's kind of weird, right? I mean, stuff is made out of atoms, but for thousands of years, tens of thousands of years, hundreds of thousands of years, human beings didn't know that atoms existed. But people in, say, the 19th century could work out, elasticity theory. They could do engineering. They could look at bending beams. They could build stuff. They did that without even knowing that atoms existed. In fact, it's very, very hard to be able to see atoms. And yet, when you describe matter, you see the phenomena that are the emergent properties of collections of atoms, but you don't know where they came from. So back in the 19th century, people invented fluid mechanics, the Navier-Stokes equations of fluid mechanics. People studied elasticity theory, and they figured out how to understand elasticity and what happens when you bend beams and you build buildings and look at the compression and all of those things. But they didn't know that they were made out of atoms. They made theories of them that didn't even mention atoms. And so you have different levels of description of the universe. There's the atomic level of description. And if you know about atoms, that's where you might start. But if you're living in the 19th century, you don't know about that. You use what's called continuum mechanics to study matter. You're looking at solid and fluids as if they were made of just stuff smeared out like peanut butter. Okay, so this idea of the level of description is something that's very important for us in this course. So the fact that you can get by, you don't need to know anything about the atoms and the springs to make models of how matter behaves. That's why it took so long for atoms to be discovered. And so where do atoms and their actual interactions come in? We can see atoms, we can measure the forces between atoms. Surely those things have a macroscopic consequence. And the answer is yes, they do. So if I want to compute, say, the shear modulus of a piece of metal or something like this, I can, in principle, work it out from, say, quantum mechanics and simulations, but I don't have to do that. I just know from, by thinking about the phenomenology of a material, that it should have properties that tell you how strong the springs are, which is roughly what the shear modulus is telling you. And then those are just parameters that you can measure in a 19th century physics description of the world. And in a 21st century description of the world, you can actually compute these things from quantum mechanics. But the thing about this is that when you think about how we describe the universe, we have different levels of description where we do that at. So let me ask you this. How many people here have taken a chemistry course? Okay, everybody's done chemistry, right? Does anybody like chemistry? Yep, some people do. Okay, good. Thank goodness for that. Right? Okay. But here's the thing. When you were taught chemistry, were you were taught, well, we have the mass of the proton, the mass of the hydrogen atom, and so on. If you want to know what the mass of a molecule is, you can just add up the mass of the atoms. Okay. When you did that, did you have to worry about the mass of the top quark? Okay, it seems ridiculous. Chemistry was invented in the latter half of the 19th century. Certainly nobody's going to know about quarks. They weren't discovered for another 100 years. Okay, and yet they were able to make a perfectly good science of chemistry without ever knowing about quarks. Okay? So it didn't matter. It just came in that, okay, the mass of the proton is blah, blah, blah. Whatever it is, the charge of the proton is blah, blah, blah. That's what it is. The spin on the proton is blah, blah, blah. That's what it is. All of that comes from the stuff that's inside the proton. But you never have to know about that. You just say, okay, well, we've got the mass of the proton. Let's go on. So that's what I mean by phenomenological parameters. So you have the shear modulus of a material is just a phenomenological parameter. The mass of a proton in chemistry is just a phenomenological parameter. If you know quantum chromodynamics, the modern theory of the strong interactions, you can actually compute, not really analytically, but using lattice gauge theory, you can actually compute the mass of the proton. In fact, even understanding the size of the proton and the spin of the proton is still a bit of a puzzle, and people still work on that. But all of these things can, in principle, be understood from a lower level of description. Okay, now this picture of the elasticity leads me to the topic of rigidity. So if I've got a material like this pen, I was able to move it because it stayed rigid while I pushed it. Okay, that's the rigidity of the material. Okay, now emergence always leads to a phenomenon called generalized rigidity. So we can talk about rigidity not just in terms of pushing atoms around, but we can talk about rigidity in terms of looking at the phase of the wave function that characterizes a superfluid. Or we can look at the rigidity of a superconductor or Bose-Einstein condensate. So there's quantum mechanical versions of rigidity that are the analogs of just the simple rigidity that you're familiar with everyday classical things. In other subjects, such as, say, biology or sociology or ecology or economics, the collective behavior gives rise to emergent properties, and there you might call those things resilience. Okay? You might have a population of insects, and you might be having some predators coming around, like birds, or you're spraying the insects with some nasty chemicals, something like this. So the question then is, how resilient is that population? Will it die out very quickly, or will it be able to survive and exist and be respond to the perturbation? So this idea then is of systems being resilient. You are resilient. If you get an illness, most of the time it doesn't kill you. You get sick for a few days, and then your body figures out how to respond to it, and then you get better. That's an example of resilience, and it's an emergent and collective phenomena to do with the way that your body regulates its behavior. Okay, so what have I just told you? What I've told you is that emergent levels of description absorb the properties of lower levels of description into phenomenological parameters, typically a small number like shear modulus or the mass of the proton. This makes fundamental physics hard because one goes against the flow of emergence. So let me draw a picture. So here is the macroscopic event, like this. And here is the microscopic world. And what reductionism says is take the microscopic world, say the world of atoms, and then use, say, statistical mechanics, quantum mechanics, or whatever, to deduce the properties of the macroscopic world. But it's not like that. The reason it's not like that is because if I take that picture of the springs, I've got the little red blobs that are the atoms. I didn't tell you what were the atoms. I didn't tell you what they're called. Okay, so that the macroscopic properties of that thing would be the same if regardless of what atoms I used. I might have different values for the shear modulus or different values for the spring constants and so on, but the basic physics would be the same. So actually, there isn't just one microscopic world. There's multiple versions of reality at the microscopic level. And if you take those worlds and then use statistical mechanics and quantum mechanics to work out the macroscopic behavior, you will see the same macroscopic phenomena. This is in fact how, in the 19th century, people made perfectly good models of the macroscopic world, having a completely wrong model of the microscopic world. They thought the microscopic world was just stuff like peanut butter. Turns out it's not like that at all. It's atoms and things like this. And it's not even atoms. It's stuff inside the atoms and the stuff inside the stuff that's inside the atoms, all the way down to superstrings if they exist and all of those things. So actually our picture of the world is more hierarchical like this. And what people who do fundamental physics, so-called, like statistical, like high energy physics, elementary particle physics, what they try to do is they try to start off in the macroscopic world and go down in scale, in spatial scale, time scale, and go up in energy scale. That's why, if we want to understand stuff that the hardest stuff in the universe to understand, you build a tunnel 17 miles long under the Swiss Alps, and you fire particles together at the speed of light and smash them up, and from the bits that fly out, you can deduce something about the high energy physics at very small scales and very small time scales. But even if you know that stuff, the trouble is this: if you start at the macroscopic world, how can you tell which of these microscopic worlds are the ones that you could have? You don't know. So back in the 1960s and 70s, how many people have heard of the Weinberg-Salon theory of the electroweak interactions? The second unified field theory. Okay, you heard of electricity, right? Heard of magnetism, right? James Clerk Maxwell realized that electricity and magnetism are the same thing, and he made a theory called electromagnetism, which you've all taken. You all know about electromagnetism. Okay, so now you've got that. Then in the 20th century, people discovered the weak interactions, which cause beta decay, the strong interactions, which are like quarks and things like this. They discovered these things. And then in the 1960s and 70s, people started to realize that the weak interaction and the electromagnetic interaction, which electromagnetism has already been unified, they are actually the same theory. So electricity, magnetism, and the weak interactions can all be unified into one theory. So, and of course that theory was confirmed, and you've all heard of the Higgs boson, and so that was a part of our modern understanding of the standard model of particle physics. The thing is this: back in the 1960s and 70s, when Weinberg and Salam and other people were trying to come up with a unified theory of the standard model of particle physics, there were many versions of this that they wrote down. Sometimes the same authors wrote down multiple conjectures about this could be what the high energy physics is like, or it could be this, or it could be this. And then it turns out that you do experiment and you discover that it's this thing over here, that's the one that actually is the one that nature chose, for reasons that we don't really understand. Okay? So there's no unique way to go from the macroscopic world to figure out what is microscopic. Okay? So that's high energy physics. Statistical mechanics, condensed matter physics, biological physics, and so on. This is reduction going this way. Reductionism is the idea that you find out what stuff is made of, and then once you've got down to here and found out what it is, then you just reverse up this thing, and then you can find out what's macroscopic. Except it doesn't work that way, because there's many versions of this, and how you get from here to here is not at all obvious, as we've talked about. So emergence, statistical mechanics, condensed matter physics, biophysics, and so on, they're all going in the other direction. And they're going in the other direction, it's actually easier. You can try to figure out what is microscopic, and it turns out in many cases, it literally doesn't matter what the microscopic world is. As I told you, when you do chemistry, you never knew about the quarks. You never had to worry about the radiative corrections to the mass of the top quark that come from gluon processes in quantum chromodynamics. Nobody knows anything about that. They just said, okay, fine, here's the mass of a proton. So reductionism is kind of doomed, because you can always keep asking, well, what's below all that? But the collective properties of matter need to be understood. And the great thing about it is, to understand the stuff that you're interested in, you don't need to know about stuff all the way down. You can do chemistry without having to know quantum chromodynamics. If to do chemistry, you had to know about quantum chromodynamics and superstrings and stuff like this, we'd never be able to do science. So this phenomenon is why we can even do science at all. Okay. So, all right. So that's that. I want to talk a little bit about what emergence is. So emergence is associated with loss of uniqueness. So what do I mean by that? if you take a fluid, particles bouncing around in a box, such a gas or a fluid or a liquid, as you lower the temperature, you get a new kind of state that emerges, the solid state. It doesn't mean that the fluid state can't exist. It's just very much less likely than the solid state. So that's what I mean by saying emergence is associated with loss of uniqueness. The phase transitions separate these states, and collective properties arise in emergent states. And I just listed some of these here: crystals, magnets, supernovas, Hall effects, turbulence, gravity, life. How do molecules come to life? A very interesting problem. Okay, so let's have a look at then at what emergence is and what is complexity. So the way we've been talking, you might say, okay, well, we know that stuff is made out of atoms. Atoms form materials such as silicon and stuff like that, so you have condensed matter. But you can also say, then look at atoms and say they form things like cells. So you can imagine cell biology, and then you can look at cells and they will form collectives, multicellular organisms like us, biofilms, things like this. And then you can look at ecosystems, community structures, social systems, and economic systems. All of these things are examples of emergent phenomena that start off at the level of atoms. Everything is built up of atoms. All these atoms behave very differently depending on how they're put together, depending on the context in which they live. And some of these systems are indeed complex. So emergence begins with strongly interacting condensed matter. True or false? Well, it's really false, because let's go and drill down into atoms. Okay, so there we are. Let's move atoms up to here. So here's condensed matter, cell biology, and so on. Now, when we look at atoms, I have to all my nucleus, I have to all my quarks and gluons, strings, and all sorts of things like that. All of those things are also emergent. When string theory was developed, people said this is the ultimate theory of everything. We can understand everything. Then they discovered that there's 10 to the 500 different ground states for string theory. So that means it's not unique. It means it's emergent as well. So every theory that we have of the universe is emergent. Okay, so here's what emergence is not. Emergence is not things that are surprising and unpredictable. In fact, we can predict emergence perfectly well. These are some of the things that philosophers of science have proposed. Sometimes people say emergence is the whole is greater than the sum of its parts. That's also not true. So if I have a non-interacting system, it has an energy which is the sum of the energy of the individual parts. Okay? But individual interacting systems also have an energy that is not the sum of the energy of the interacting particles. So let's take the atoms in a fluid. Okay, the atoms in the fluid have potential forces between them. But because they're close together, I can't just simply write the total energy as the sum of the energy of this atom and the sum of the energy of this atom and the sum of the energy of this atom, because they actually affect each other's energy. So they have an energy that is collective, but it doesn't necessarily result in emergent behavior. It doesn't necessarily. It can do, but it doesn't have to. So a gas with a modified equation of state compared to the ideal gas is still a gas. Okay? So it's not just the whole is greater than the sum of its parts. The main thing about emergent properties is that they have generalized rigidity, which is an outcome of the collective interactions between the components. And it's this is in some sense the defining characteristic. The fact that this pen could move when I pushed it, whereas the air could not, that is the signature of emergence. Okay, now I'm going to skip this. This is I want to skip phase transitions. I want to talk about what we will discuss in this course. So in the course on phase transitions, everything that we did there is focused around this point here. This is temperature. This is the magnetization of a magnet. When we look at M, we're counting, here's a magnet, it has little spins. Some of the spins point up, some of the spins point down. If more spins point up than point down, it is magnetized and it will stick on the door of your refrigerator. If you raise it to a temperature higher than this critical temperature, then all of the spins either pointing up and down, there's an equal number pointing up and down. At this temperature, it will not stick to the orbital figure. So you have magnetization occurring in a continuous way as you go below the critical temperature. And that was what we talked about last quarter. Now, this is the problem with phase transitions, universality, critical phenomena. Now, what we're interested in this course is we're interested in what happens at low temperature, right away from the phase transition. And it turns out that once you go well below it, then you also have a regime of behavior where it's universal. It doesn't depend too much on the details. There's various aspects of matter and how it behaves, which don't really depend on the details. They just depend on symmetry. So hydrodynamics, the excitation spectrum, topology, all of these things are things that emerge at low temperatures from matter. And that's what we're going to be focusing on in this part of the course, in this part of these two courses. All right, let me give you some of the universal outcomes of emergence. So what we will focus on in this class is that emergence is associated with a breaking of symmetry. So a magnet has high temperatures, the spins can point up or down, and they can point in any direction. You have full rotational symmetry. With low temperature, they form a magnet. They all point in the same direction. So they've broken the symmetry. This idea of symmetry breaking is a fundamental aspect of emergence. When you have emergent order, then you can have holes in the order. You can have defects. In other words, you can have a system which has order, but there's a hole in the order, a breaking of the order. So, for example, you might have a crystal. Missing the element. This can arise, and it is called a dislocation, and it's a kind of defect that you might have in a crystal. If you look at any of the metals in this room, look at them under a microscope, you'll see that the atoms are not perfectly ordered. There's places where an atom is missing. There's places where there's local regions of disorder, and so you have all sorts of defects in the system. And if you understand what is the order that the system can have, then you understand what are the defects it can have. Now, these defects themselves can be topological, and we'll talk about that. And because they're topological, they actually can themselves order, and then that order of the defects of an original order can then also have defects, and so on and so forth. So the theory of the quantum Hall effect is a theory about stuff that orders, but can have a defect in that order. The defects in that order can themselves order, but that order can have defects, and so on and so forth. There's a whole hierarchical picture of topological objects ordering and having disorder variables that then can themselves order, and so on. This idea of condensation and order of dynamical degrees of freedom is the cornerstone of condensed matter physics. The other thing about these systems, about when you have emergent states of matter, is that you have low energy excited states. So you've all heard about the Higgs boson. So the Higgs boson is a universal aspect of certain types of field theory. And it has to exist. It doesn't just exist in elementary particle physics. It exists in superconductors and other systems. These particles exist because of the certain ways in which symmetry is broken in emergent phenomena. So people need to study what are the generic types of excitations, the generic types of particles that can arise, and those can be predicted without needing to know very much about the system. Okay, so let me just see if I want to talk about this. I think I'm going to skip this part.
I want to talk about computer simulation. Okay, so why am I changing gears here? Well, okay, let me do it this way. Well, I have another 10 minutes or so. Here's the Nobel Prize in 2016. David Fallows, Mike Koslitz, Duncan Haldane, all British physicists, in fact. They were Mr. Thatcher's gift to American science by defunding science in the UK in the 70s and 80s. Many people, including me and others, moved to America. These people, a bit older than I am, they won the Nobel Prize in 2016. Let me tell you what they did. Okay. So we're going to talk about superfluids in this course. So let's talk about a normal fluid. So the one on the left is honey. It's a normal fluid. It has viscosity at room temperature. It's tasty. The one on the right is a superfluid. It has no viscosity, roughly speaking, at 1 degree above absolute zero. And there's a picture there from the movie that is on this class website, telling you about the properties of superfluids. And this is a thing called the fountain effect. Okay. So that's the superfluid. Basically flows without viscosity. So what Mike Koslitz and David Fallows did, their part of the Nobel Prize, was to ask the following question. Let's take a bunch of arrows on a plane and let's orient them in such a way that they minimize their energy. So they figured out ways to do it, and they discovered that you can have them all pointing in the same direction, but you can also make a situation where they all go around like this, and they do this as you go further and further out. That is a configuration of atoms in a plane, and that is called a vortex, because it looks like something is flowing in this direction. And you might ask, well, what's happening here in the middle? Well, here in the middle is a kind of singularity. And this thing here in the middle is an object that behaves like an elemental particle, but it's actually a topological object. But it just exists because you can create a configuration of arrows on the plane that look like this. What they did from this piece of work was, and we'll talk about it in this class, was they discovered that a superfluid has a kind of rigidity. It's a fluid, so it doesn't have the rigidity like I was showing you here. It has a rigidity of its wave function, a quantum rigidity. And they worked that out, and they predicted how that rigidity for different superfluids depends on the temperature where the fluid becomes a superfluid. That's this piece here, and then here's the experimental data, and here's the theory that goes on for the experimental data. Well, the thing about this is that a superfluid is a pretty complicated quantum mechanical object. A superfluid in 2 dimensions is even more complicated, and they figured out how the superfluid forms just by thinking about the simplest way that atoms could exist on the plane energetically. They didn't worry about anything to do with the atoms or even quantum mechanics. Okay? And it's amazing that they were able to make this prediction. So you've got a very simple model here, laughably simple, that can predict very complex phenomena. And in fact, everything we know about the physical world comes from looking for the simplest mathematical models, and that's how we have such great explanatory power in physics. Now, let's talk about computer simulation. I'll end with this today. It won't take very long. Leo Kadanoff is a theoretical physicist who worked on the theory of phase transitions in the 1960s. And let me put this back up here. And after he did that, at my previous university, in fact, the University of Illinois, he then moved to Brown University and studied urban planning. He tried to apply physics to society. And he says this: at the time, there was a great national push towards understanding the dynamics of urban development. Jay Forrester at MIT had developed a computer model of urban change, which took a very simplified view of an urban society. And he used the output of that model to prescribe social policy. I did not like that social policy. Okay. So He set out to use the same modeling tools that Forrester had used to reach conclusions which were more to my liking. The first result was that while not changing the model at all, we could reach opposite conclusions from that of the MIT group. Then we went on to build other models, which more accurately recorded our own prejudices and points of view. But after a while, we realized the following. If these models really represented little more than we could say in words, why not just leave out the computer? Okay? So he realized that he was just putting in the answer. So the construction of this sort of model seemed to be a rather pointless endeavor. For this reason and others, I moved away from urban studies. In fact, he went to the University of Chicago and then started working on chaos theory and turbulence and all sorts of things like this. Okay, so here's the moral of the story. When you do a computer simulation of something interesting, there's two things you can use a computer for. One is to get numerical information that verbal arguments cannot address. So you make a computer model of a system, say a society. And then you might want to ask the question, well, how rich is that society going to get? How much economic output is there going to be? You want to know, is it going to be just $3 or is it going to be $3 million? Okay? The numbers matter. If you want to do that, you might well use a computer to make an accurate model of something that you can state verbally. But really, the best use of a computer is to find the emergent phenomena, because those are things that you don't put in. You simulate what you think is there, and then what you observe coming out is stuff that you hadn't expected. That's the best thing that you can do with a computer simulation. So like in my group, we use computers, when we use them at all, to understand things that we haven't put in by hand. And that's the purpose of computer simulation. Okay, I'm going to stop there. So there's more to say about this, but I'll go on to something else next time. Any questions anybody have from the audience about what we've talked about today in this very, very superficial overview of the things we're going to be discussing?